Okay, so today we're going to talk about drawing angles in standard position. We're going to find the arc length of an arc on a circle. Then we're going to convert from degrees to radians and radian to degrees, and we're also going to find the area of a sector of a circle. So some of this is a review from geometry. Some of it will be new. But basically, an angle in standard position is this. It's made up of two rays, and the two rays are drawn from a common vertex. Okay, and those two rays form an angle. One ray is called the initial side, and then that side stays fixed on the positive x-axis. And then the other side, rotating side, is called the terminal side of an angle. If the rotation is in a counterclockwise direction, then the angle is positive. If the rotation is clockwise, then the angle is negative. Lowercase letters, Greek letters. So we use certain Greek letters such as alpha. That looks sort of like a fish. I'll do that a little bit differently there. That's alpha. Beta is like a bee with a tail. We can use theta. Theta is like a circle with a line through it. Alpha, beta, theta. Sometimes we use things such as gamma, which looks like this, are often used to denote angles. So I have a couple of pictures here. The initial side, you can kind of picture a coordinate plane being here. The initial side of an angle in standard position is always on the positive x-axis, and this side is fixed. So the other side is called the terminal side, and that rotates like the hands of a clock. This one is rotating counterclockwise. It goes about halfway through the first quadrant, so that would be a 45-degree angle. If you rotate the other way, so I'll put this coordinate plane here, your initial side is still on the positive x-axis. That is fixed. That doesn't move. The rotating side is called the terminal side. So this one rotated in a clockwise direction, like the hands of a clock moving clockwise. So that's a negative 45-degree angle. Okay, so we'll draw some angles in standard position. The first thing you want to do is draw a coordinate plane. Then you put your initial side on the positive x-axis like that. So remember, this is 90 degrees. Each quadrant's 90 degrees. This represents 180 degrees. This represents 270 degrees. And this represents 360 degrees and also 0 degrees. So if we want to do a 45-degree angle, that would be about halfway through the first quadrant. So we make an arrow showing which way we rotated. So we rotated counterclockwise, and we write 45 degrees. And that's how you show an angle in 45 degrees, an angle of 45 degrees in standard position. The reason why we draw the angle is this. I could have rotated the other way. So if I showed my rotation, and this is going to be kind of new to you guys, if I show my rotation going clockwise, that's actually a negative 315-degree angle. It went 90 degrees through the fourth quadrant, then 90 degrees through the third, and 90 would be 270, and then another 45 would be 315 degrees negative. So if you don't draw the arrow 45 degrees and negative 315 degrees, look exactly the same. So let's draw a negative 90-degree angle. So we start with a coordinate plane. We draw our initial side on the positive x-axis. That stays. Negative 90 degrees means I'm going clockwise. So I would go clockwise like this, draw a little arrow. There's my terminal side, and I would write negative 90 degrees. Again, the reason that the arrow is important is that if I drew my arrow going the other way, that would be a 270-degree angle. Okay, 225 degrees. What would that look like in standard position? So I am putting my initial side on the positive x-axis. So if I go this far, that's 90. If I go this far, that's 180. So I need 45 more degrees, which would be partially through this quadrant. That would be a 225-degree angle. And again, the arrow is very important to show which way you went. Now, this is where things are going to get different than you knew in geometry. We do have angles. We're dealing with negative angles. We're dealing with angles that are bigger than 180, 225. You never really dealt with an angle bigger than 180 in geometry. But we actually can go thousands of degrees because that hand, that terminal side that rotates like the hand of a clock, could go around multiple times. So for example, 405 degrees. 405 degrees in standard position. So I'll draw my initial side on the positive x-axis. If I rotate it all the way around once, that's 360 degrees. But I want to go 405 degrees. So how many more do I have to go? If it's 360, and then, so I have to 405 degrees, I would have to go another 45 degrees because 360 plus 45 is 405. So I went all the way around once, and now I have to continue another 45 degrees, which would be halfway through the quadrant. So that would be 405 degrees. So I need that arrow to go showing that I went around once and then another 45. Because if you look at this picture and you look at picture A, the 45 and the 405 would look very similar if it were not for the arrows showing that I went around the circle 360 and then another 45. Okay, let's look at finding arc length and what arc length is. I cut off my PDF a little bit, but for a circle of radius r, so any radius r, a central angle of theta, so there's that Greek letter theta, radians, subtends an arc whose length s is this. S equals r times theta. Okay, and the thing that you have to remember is S stands for arc length, so S is arc length. R is radius, and theta is the central angle, and we'll review that a little bit, in radians, because in a little while we're going to learn how to convert between radians and degrees. So it says, find the length of an arc of a circle of radius 4 meters subtended by a central angle of 0.5 radians. So radians is just another way to measure an angle. So what we're looking for is this. We have a circle, and the radius of this circle is 4 meters, okay? So I'm going to put another radius here also of 4 meters. This is what we call the central angle, theta. Okay? Theta is measured in 0.5 radians. So that's a decimal 0.5, if I could fit my decimal point in there. Let me erase that a little bit. This angle theta is 0.5 radians. Again, radians is just another way to measure an angle instead of degrees. And when we say the arc length, we're looking for the length of this arc. This arc is part of the circle. So this is S, my arc length. So if I have a circle of radius 4, and I take those two radii and I make an angle of 0.5 radians, how long is that arc? Okay, so this is the way we measure round things in geometry or trigonometry. You did have a way of doing this in geometry, but it's a little different now. So S equals R theta. So R is 4 meters and theta is 0.5 radians. So 4 times 0.5 is 2 meters. So it will be in the same units as the radius. So what it's saying is this arc length, and I'm now going to highlight it again in purple. This arc length that we just found would be 2 meters long. Now let's learn a little bit more about what a radian is. So 1 revolution around the circle is 2 pi radians. So that comes from basically the circumference of a circle. And we look at if the radius were 1. The circumference of a circle is 2 pi r. And since the radius is 1, the circumference is 2 pi. So when we speak about radians, we're essentially talking about the length of the arc all the way around the circle, which is the circumference. If the radius were 1, that circumference would be 2 pi. So 1 revolution around the circle is the circumference of the circle. If a circle is of radius 1, that circumference is 2 pi. So half the circle, 180 degrees, is equivalent to pi radians. If all the way around the circle is 2 pi, 180 degrees, or halfway around the circle is pi radians. 1 degree is equal to pi over 180 radians, and 1 radian is equal to 180 over pi degrees. Essentially, pi over 180 or 180 over pi is what we call a unit measure, because 180 is equivalent to pi. It's a unit fraction. 180 is equivalent to pi, so if I do pi over 180, it's essentially 1, or 180 over pi is essentially 1. So converting radians to degrees and degrees to radians is a pretty simple concept. If I have a degree measure and I want to convert it to radians, let me put this up here. The degree is equal, let me erase that. The radians are equal to the degree times pi over 180. So if I want to convert 30 degrees to radians, I simply multiply it by pi over 180. And, of course, reduce your fractions. So that's 30 pi over 180. 6 goes into 31s. 30 goes into 31s, 30 goes into 186, so it becomes pi over 6 radians. So 30 degrees is equivalent to pi over 6 radians. So when we refer to angles, sometimes we'll refer to it as the degree measure, sometimes we'll refer to it as the radian measure. The radian measure is pi over 6. So if I do 120 degrees, I do 120 times pi over 180, which is 120 pi over 180, and then I begin to reduce that. So I'll cancel out the zeros, and then 4 goes in, there's the bell, 4 goes into 120 3 times, and 4 goes into, let's do that again. 6 goes into 12 2 times, and 6 goes into 18 3 times. So it's 2 pi over 3. So 120 degrees is equivalent to 2 pi over 3. So when you have a negative angle, it doesn't change the fact that it's still negative when you convert it. You do negative 60 times pi over 180, which is negative 60 pi over 180. So an angle that's negative in degrees will be negative in radians. I'll cancel out the zeros. And this reduces, 6 goes into negative 6 1 time, and 3. So it's negative pi over 3. Okay, for sake of time, I won't do this one. But sometimes it's ugly, but that's okay. You just reduce your fraction. So 104 times pi over 180 is 104 pi over 180. And then you start reducing as much as you can. Simple math, divide them both by 2, and then you can divide them both by 2 again. So it's 26 pi over 45, and that's about as much as you can reduce that. So now going the other way from radians to degrees, you simply take the degrees are equal to the radian measure times 180 over pi. So you take pi over 6 times 180 over pi. You should know the answer is 30 by A above, but I want to show you why. You cancel the pi's, you get 180 over 6, which is 30 degrees. So pi over 6 is equivalent to 30 degrees. Pi over 3 will be 60 degrees, if you can see from part C above, but I take pi over 3, I multiply by 180 over pi, cancel the pi's, I get 180 over 3, which is 60. So pi over 3 is equivalent to 60 degrees. Now, your radians don't always have to have pi in it. 5 radians is fine. You simply do 180, 5 times 180 over pi. And in this case, you would actually get out a calculator and do it in decimal. So if your radians don't have pi in it, you just do the decimal equivalent. So I actually take out a calculator, I do 180 times 5, and I divide that by pi. Make sure you find that pi button in your calculator. Don't use 3.14. So we get 286, and we're going to have to round it. So we'll do 1 decimal place, 286.5 degrees. So if your radians don't have pi in it, your answer is actually going to be in decimal. There'll be a decimal. And then last, 9 pi over 4 times 180 over pi. Again, we cancel the pi's. 4 goes in here once. 4 goes in there 45. So then I have 9 times 45 is 405 degrees.